Hi, I'm Kevin Donnell, and this is a lecture on sentence embeddings. So in this lecture, we're going to cover a couple applications of sentence embeddings, define them, show their purpose, give a brief history of sentence embeddings, dive into transformers, as well as BERT, and understand the training process of BERT, and then get a deep dive into how BERT produces transformer-based embeddings. So at a high level, what are sentence embeddings useful for? Everything from semantic search, like in Google, sentiment analysis, organizing things between negative, positive, reviews, content recommendation systems, sort of newsfeed systems, Q&A systems, retrieval augmented based generation systems, and clustering in different types of tools, including Latent Lab. So embeddings exist to help computers understand language at a very high level. If we ask a question of how are you to a computer, it simply can't understand that. But if we have this intermediate representation, a numerical representation of this language, we can actually interact with computers. And we can do this with things in addition to language. For example, we could embed the concept of a house and use that in a computer model to predict the value of different houses. In this case, you can notice that the values in the vector are actually interpretable. We know that we can map them to things like square footage, bedrooms, and bathrooms. But if we come back to the language, it's not actually as interpretable. So trying to understand where do these things come from, how do we produce them? There's plenty of libraries out there, APIs as well, that can produce sentence embeddings. And what we're going to dive into in this lecture is sort of going under the hood of the OpenAI's embedding API endpoint. But there's also the sentence transformers library from Hugging Face that makes it super simple to run embedding models locally, as well as community provided embedding models. So a brief history of sentence embeddings. So Claude Shannon was the first person that sort of tackled this problem of trying to understand patterns in language. And he represented text as vectors. And so this comes from his PhD dissertation on n-grams, where he used them to encode sentences by counting the sequences of words capturing basic context statistically. This paved the way for later representations, such as word2vec, which is actually the combination of two different models, continuous bag of words, and skipgram, which are both shallow neural networks. Continuous bag of words is used to predict the center word from surrounding context, whereas skipgram does the exact opposite, where you start with a single word and try to predict the surrounding words around it. And once we have these word embeddings, we can plot them and view them in vector space and operate over them. So for the example, if we add the difference between the vectors of woman and man and add them to king, we roughly get the vector location of queen. And so this suggests that there's a direction in this vector space that encodes the concept of gender. However, if we look at individual word embeddings, it's not always enough. If we take these examples, so I went to the riverbank and I went to the savings bank, having just the embedding for the word bank doesn't capture the context of what sort of bank we're referring to. And so if we come back to methods for sentence embeddings as we sort of progress through history, neural bag of words was one approach to try to capture the context of a sentence. However, we're just averaging across all of the individual word embeddings to a full sentence embedding. And this still does not fully capture the context of what the bank, or if we were to use the word riverbank in this situation, would fully capture that. So it's still ignorant of contextual information. So transformers architecture changed all of this. And so now each word listens and adapts based upon the context, much like people do when we're interpreting sentences. And so this was originally invented to combat the slower training times of recurrent neural networks and long short-term memory networks that were being explored as alternative neural network methods prior to the transformer architecture. And so what we can think about the real value of a transformer lies in its ability or its attention blocks. And so this context comes from this attention block. And what we're really understanding is the influence of all words, and all words are tokens, and we'll get to what tokens mean in a bit, but the influences that these words have on each other and basically encoding that representation from this attention mechanism. And so the transformer can be broken up into two separate blocks. an encoder and a decoder. The attention mechanism in the encoder is bidirectional, which we'll get to the importance of that later, and it's unidirectional in the decoder. Um, and so the decoder is simply just predicting the next word. So using previous information from previous tokens to produce a probability distribution over a vocabulary on what is the next most likely word. Whereas in the case of the encoder, we're taking in a sequence of text and then in parallel converting those to representative embeddings that encode the context of all the surrounding words for each one of those tokens. And additionally, there's a special token involved there called the classification token, which we'll get to, which encodes the entirety of all of the sequence that's being passed in. And just to point out these connections between the two blocks, these are actually cross-attention layers, which are a result of sort of the initial use of why the transformer architecture was created by Google, which was for machine translation. So if you were to train this on sort of Spanish to English translation, this is carrying over the Spanish context from the initial embeddings in the encoder when we are trying to produce the English translation, which I have an example of I'll show in a second. And so to sort of step through one by one how this works, we'll pass in a sequence of tokens on the left. I went to the riverbank, and then on the output side of the encoder, we'll get a embedding for each one of these tokens. And we would actually get an embedding for this classification token on top of it, which encompasses all of these tokens as well. Again, we'll get deeper into this as we go on. And then looking at the decoder, we would start by passing in a special token, this beginning of sentence token, pass it in, and we get this first output, again, from the cross-attention layers because we're getting the context of the phrase, I went to the riverbank in English passed in. We get the first predicted response of the first Spanish token, fui. We append that to the beginning of sentence token, and this is the autoregressive nature of the decoder where we pass in beginning of sentence, fui, and we get and then this process continues to get fui a la orilla del rio, to get I went to the riverbank. And so with these units, sort of these encoder and decoder blocks, we can build very common things that we see around us now. So BERT is a stack of these encoder blocks, which stands for bidirectional encoder representation from transformers. And there's two common sizes, BERT base, which is 12 of these encoder blocks, BERT large, which is 24 of these encoder blocks. And then GPT, which generative pre-trained transformer, is a stack of decoders. So when we're passing things into GPT, any of the sort of GPT variants, what we're doing is passing it into a stack of these decoders. And typically, what exists is more than just that beginning of sentence token, but typically some system prompt that says that you are a helpful agent, and sort of what follows is a discussion between you and some user of this system. And so it's already primed to respond to what your input is, which is appended to that initial system prompt. And so GPT comes in various sizes. The original one, GPT-1, was a stack of 12 of these decoder blocks. 2 scaled up to 48, 3 was up to 96, and GPT-4, we still don't have, we don't know for sure what's there's no publicly shared number for the stack of decoder blocks in GPT-4. So looking at this in a bit more detail when we're running through inference, when we pass the sentence, I went to the riverbank into BERT, which again is a series of these encoders, we would first prepend it with a special token, this classification token, as well as this separation token to identify the end of a sentence. And what's happening is that with these 12 or 24 different encoder blocks, we're picking up local features, basic syntax early on in some of these earlier blocks, and then more of a global context and semantics in these later blocks. And the output, as I mentioned before, is we get an embedding for each one of these words that has context. So bank in this, the embedding for bank here would have the context of it being a river bank, as well as this classification token that has a sentence embedding that captures the entirety of this sentence or the sequence here. And so in the case of the BERT base model, this is a 768 value vector here. And what we're going to look at now is sort of treat BERT as a black box, sort of these stack of encoder models as a black box to walk through the training process of BERT, pre-training. Well, so that training process is split into a pre-training phase as well as a fine-tuning phase. And so transformers initially need to be retrained for each specific NLP task, but BERT offers a solution by breaking this up into these two stages. And it gives us a general model of language through these two pre-training tasks. And so when we're pre-training BERT, we're actually doing two training tasks at the same time. One is this mass language model prediction, as well as this sentence level comparison or next sentence prediction. And so once we have this, we can then use this pre-trained model that has a general understanding of language to fine-tune it on these other tasks. So multi-genre natural language inference, MNNLI, is basically predicting the relationship class between a pair of sentences. Named entity recognition is basically identifying the types of parts of speech of different items within a sequence. And then question answer is basically passing in a passage as and identifying with a question and trying to get the answer as a result. And so I think sort of a broad way of thinking of these is this is largely unsupervised, this process of taking sort of text from the internet and sort of randomly masking text to try to predict what token is being masked, as well as predicting, is this the next sentence? And that can be done by just taking neighboring sentences from Wikipedia articles and then diverging sentences that are randomly chosen throughout Wikipedia articles. Whereas the fine-tuning stage, these are much more, these are labeled data sets. So Squad for question answering is a common one where there are passages of, I think they're SAT-based examples where we have a passage of text which contains an answer and then a question that's being asked, and the system is required to identify that context to produce the answer. And I'm going to step through a bit more of this pre-training stage, just because this is ultimately where our sentence embeddings are coming from. And so again, if we take this first example, I went to the riverbank, and then the second sentence, the water was warm. These would be our two sentences we passed in. So again, we're going to prepend it with a classification token. We're going to tokenize the words. I went to the riverbank. We're going to randomly mask one of these tokens, and I'll get into the tokenization process a little bit further down the road, but we can roughly think of tokens being equal to an individual word here. And we'll add these separation tokens in between where each of these sentences end. And so as this flows through BERT, again, treating this as a black box, during the training phase, for each one of these masked tokens, so we're looking at this first one here, the river, which is masked, we're going to get a predicted probability distribution across the entire vocabulary of the language. And then we see that river is highly predicted here, and we're going to compare that with the ground truth. We know that river is actually the answer, and we can treat it as a one-hot encoding, where river, the value of river is 1, it's true. All the other values in the vocabulary are 0. And what we're going to do is calculate the cross entropy loss between these results and back propagate these changes, the error through to the weights within the network. And we'll get into the details of what those weights are as we start to open up the box of BERT. But we're just looking at the pre-training phase now. And the same would happen for water here. So we're seeing this happen to river, water, this would also happen to. And then for next sentence prediction, we have a softmax classifier, so a neural network that will take in this classification token, again, prepended at the beginning of the sentence, and will output a distribution across, is this the next sentence or not? So is this sentence, the water was warm, this sentence following, I went to the riverbank? And again, we have the ground truth, which is encoded as a one hot encoding. Um, yes, this is a next sentence. And we compare that and again, calculate the cross entropy loss between these two results and back propagate the weight changes. And so this process is actually what forces this classification token to learn or encode all of the information in both of these two sentences, which we'll see as we go forward is extremely valuable. And so now a bit more on tokenization. So what we want to do is, or rather, the neural networks require this one-dimensional sequence. And so one thing we could do, sort of a naive approach, would be to have a binary UTF-8 encoding where there's two possible symbols, just 0 or 1. And this sentence is represented by these bits where each bit represents a character. Um, and this would kind of force us to have a very small vocabulary. Um, but these numbers are just a very precious resource. And so they're the root of what the context window is. And so there's a lot of discussions around sort of larger and larger context windows. But we can see here that this is a fairly large context to be passing in to represent this fairly small sequence of text. Um, Byte encoding is a step in that right direction. So we reduce to we have a larger vocabulary here of 256 possible symbols that we can use. And but we can take this even a step further with byte pair encoding. So what we're doing is actually looking through to identify common combinations of characters through text. And we can learn this vocabulary basically of when certain characters happen along with each other frequently, we can encode that as a unique symbol in itself. And so there's a tool available to try this out, which is Tick Tokenizer. There's an app where you can actually play with the same model that's being used in GPT-3. I don't know if GPT-4 is the exact same. I don't think that that is publicly disclosed. It's GPT-4, I'm sorry. GPT-4 uses Tick Tokenizer. GPT-4o, uses a slightly larger vocabulary set. So this is but a 100,000 size vocabulary. And just wanted to remind you that tokens are not embeddings. So we're looking at numbers here that represent the words that we're passing in, this sequence of text that we're passing in. I went to the riverbank being represented by these tokens down here from this CL 100K base tokenizer. But these themselves are not embeddings. It's almost better to think of these as symbols. They're just a representation we can point to decode this text. And so now we're going to sort of with this knowledge of tokens, open up the black box of BERT. And we're going to step through one encoder block here of BERT and see how we get to essentially a full sentence embedding for the sentence that we're passing through. So we start with this sentence. I went to the riverbank. We then break it up into different tokens, append the classification and separator tokens. We encode these individual tokens to their numerical representations or symbolic representations. And these numbers allow us actually to look up a predefined embedding for each one of those tokens in an embedding matrix. So this embedding matrix actually starts out random within BERT, and it's learned over time. So we have a vector that's associated with each one of these. So this would be I. We have this initial vector representation embedding for that word. And then we add a couple of additional pieces of information. So we have a positional encoding, which basically encodes where in the sequence this token is falling. There in the original BERT paper, they used a method of sinusoidal encoding, but in I'm sorry, in the original Transformers paper, they used this sinusoidal encoding, but in BERT, we're actually using these are learned parameters as well. So over time, throughout the training process, it's learned that this is actually the first position in the sequence. And then similarly, segment embeddings are added. So segments are everything up until the first separation or between different separation tokens. So this is just the first segment here. And these are all added together to produce this initial word plus position plus segment embedding for each one of these tokens that we're passing through. And so that gets us through to this input embedding stage plus positional encoding right before we head up to uh, multi-headed attention. If we go next. And so when we get into multi-head attention, we can actually break it down. So this is actually from the original Transformers paper, where we can think of attention in the context of these three matrices, the value matrix, the key matrix, and the query matrix. And rather than tackling all of multi-head attention at once, we can look at one single scaled dot product attention with these three matrices. So that's what we're going to step through here. And so if we step back and think about this a little bit more conceptually, what we can think of as this sort of query matrix, we can think of it as each token sort of asking a question or a query, like who influences me? So bank asks out to all the other tokens, who out there influences me? And then we have a bunch of these other tokens sort of respond in varying degrees, like River saying, like, I definitely do. I definitely influence your meaning. To and the are kind of like me too. I kind of sort of influence you. And then I went, yes, yeah, I'm part of that as well. And so this process of attention is basically encoding these different these questions and responses of how much each of these tokens influence one another. And ultimately, the result of this is that we start with these initial set of embeddings and then have this resulting context-aware set of embeddings for each one of the tokens that come out. And how this actually happens in the case of the query vector, we actually have it's a cross product between this, again, this query matrix that I had mentioned before, which is a set of learned parameters. So these are tunable, adjustable, and changed throughout that training process that I had mentioned of BERT. And we take the cross product of this matrix and the initial embedding of a given token to get its corresponding query vector. And so this is in the size of roughly 64 dimensions. I'm trying to go by going again under the hood of GPT's ADA embeddings. And just to call out real quick, it's called GPT ADA embeddings, which can be confusing because GPT really signifies that it's an OpenAI model, but that embedding model is actually a BERT-based encoder model. It is not a decoder model. Anyway, that ADA or ADA model has a dimension of 1536, and it's assumed that there are 24 attention heads in the multi-head attention, and therefore breaking that across 24 heads, those 1536 dimensions gets us down to 64 dimensions for this query vector. Stepping through, we do basically the same thing for the key. So when River responds with I influence bank, we're getting this by similarly another matrix where we have learned parameters of the key matrix, and we take the cross product of that key by this, we take the cross product of that embedding by this key matrix, and this results in the key vector for River. What we can do is conceptually think about this in this lower dimension, 64 dimension space, where keys matching queries whenever they closely align with each other in this lower dimensional space. So I'm showing 64 dimensions as sort of this two-dimensional plot where we have these vectors of both the query, this blue vector, and then the key, this green vector. So we can see that they sort of align with each other. This is sort of hypothetical and sort of hand wavy, but showing that River is affecting bank in this situation, and that they're aligning with each other in this lower dimensional space. And so that's just looking at one query vector for a single token and the key responding to that query for another single token. But we then apply this across all tokens, where all tokens are essentially asking a query of who influences them, and all tokens reply to all other tokens on how they influence them. And that results in this larger matrix here. And so we can measure how well a key answers a query by computing the dot product between all of the individual key and query vectors. And this results in this grid of real numbers with a range of negative infinity to positive infinity, giving us ultimately a score of how relevant each word is to updating the meaning of every other word. So we can visualize this as a grid of dots to kind of see at a glance what is the influence of each token on each other. And again, sort of thinking about the lower dimensional space and connecting these dots to the meaning, we can think of sort of the query from bank and then the key responding from river as being closely mapped together in this lower dimensional space, the key and query space, and other combinations as being a bit more divergent and not mapping as closely to each other in this lower dimensional space. And so in these examples where we get a very large dot and in this lower dimensional space, the vectors are aligned, we can refer to this as this token river attending to the word or token bank. And so after we've done this, we've essentially created what was referred to as the attention pattern. We then take the softmax of each one of these columns to get a distribution across all of the tokens on how they influence each one of these tokens in the column. Um, there's a little bit more nuance here because we're actually dividing by the square root of dimensions in the key query space to help with training stability. But for just the sake of simplicity here, what I'm showing is that we're now taking the softmax across each one of these columns, and we can view the attention pattern as a distribution across each token of how its attention is being paid across all other tokens. So we're also going to remove the weight matrices and the query and key vectors to clean things up and see our attention pattern before tackling this last matrix, which is the V, the value matrix. And again, kind of coming back up to the surface, if we think about sort of this input embedding, we need to update this embedding of each word given this contextual information. And so, for example, if we want the word river to cause a change of the word bank in this 1500 dimensional space, 1536 dimensional space, that more specifically encodes a riverbank, we need to create this sort of delta vector. And the way that we do this is we can sort of think of having this, is a bit of a naive approach because this isn't exactly how it happens, but I'll get to that in a second. But we can think of it as this one single value matrix, which is 1536 by 1536. And we are taking the the embedding of river and taking the cross product of the value matrix. And getting this resulting vector that would amount to the change in that initial vector of the word bank to it becoming a river bank from this embedding river. Then we take the value matrix and multiply by every one of these embeddings to get a sequence of value vectors. And these vectors are multiplied by the corresponding weight in each column of this attention pattern. And so many of these values zero out, but we can also see, for the example again of bank, we're adding a large proportion of the value vector from, say, tokens like the word river, while other tokens like the are being completely zeroed out. And so then finally, to update those initial embedding vectors that we have, we sum across these columns here to get to add together all of these rescaled values in the column to create a change we want to add to the original embedding vector. And so adding these to, and so then adding these sequence of changes to all of our corresponding embeddings provides us a sequence of richer, more contextualized embeddings coming out of the attention block. And so this whole process is one single head of attention. And the entire process is parameterized by these three different matrices, the key, the query, and the value matrix, all of which have these tunable parameters, which are learned in the training process. And the value matrix is, if we look at it, orders of magnitude larger than the key and query matrix. But we can actually optimize this. And um, the in BERT, this is actually broken up such that it supports parallelization across GPUs, and we can actually consider it sort of this low rank transformation of two smaller vectors, sort of this value down, which we can think of as sort of projecting from this um, weight value from the 1500 dimension space down to the 64 dimension space, and then this weight up matrix that goes from the 64 dimension space up to the 1536 space. And so again, this is just one single head of attention. If we look across the entirety of multi-head attention, we we have a much larger set of attention patterns here. And so the idea here is that each one of these attention heads, self-attention heads, would learn basically a different perspective on how the tokens influence other tokens. Um, and so each one of these heads, as I mentioned, has its own attention pattern, which are essentially its own proposed changes to the token embeddings in each one of the positions. And so if we sum together all of the proposed changes, one for each head, and add to the original embedding, in this example at the bottom here, we get sort of one slice, one single embedding that is changed um, out the other side of this multi-head attention block for this word bank. We start with this initial embedding, and then we have all of these deltas that are created for from each one of these different attention heads. And something to note here is that this is fairly large. And so that many embedding models will actually only compute this CLS token at inference time. And they'll apply attention normally during training, but to optimize the inference speed, and will only compute this classification token so that you get the sentence embedding, as opposed to an embedding for every single token that you're passing in addition to the sentence embedding. And again, just kind of thinking about how large these things are, BERT base has 12 attention heads. The larger BERT has 24 heads. ADA embeddings from OpenAI, it's not publicly disclosed how many attention heads they use, but again, it's widely speculated that it's 24 attention heads, which also gives us that resulting 64 low dimensional space from the 1536 dimension high dimensional space, because we're dividing by how many attention heads the key and query matrix are being mapped down to. And then it's just to kind of throw it out there, this is in the context of the decoder block, but again, multi-headed self-attention exists in the decoder block as well. It's pretty wild to think that GPT-3 already has 96 of these heads, and it's not yet confirmed how many exist within GPT-4 and other variants of GPT models. So now moving on to this add norm of the encoder block, the original input embeddings with the positional encoding are added back to the output of the multi-head attention block. We can think this is a skip connection, basically, that helps prevent information loss and stabilizes the training process. Then layer normalization is added to each one of these tokens independently. And this is done by subtracting the mean and dividing by the standard deviation across its embedding dimensions. And then we finally arrive at this. So we have sort of updated token embeddings after the add normalization process. And now we move to the feed forward neural network. And this feed forward neural network typically consists of two linear transformations with a nonlinear activation function in between. So that first linear layer expands the input dimensionality from that 1536 space, typically to 4x, So in this case, 6,144. Um, and that's then followed by a nonlinear activation function like ReLU. Then the second layer projects it back to the original dimensionality, so the 1536. And this design allows the model to capture complex patterns and interactions within the data. There's actually interpretability research that's ongoing that suggests that this is where facts are actually stored within these models. So things like that Van Gogh is a painter could live in these feed-forward neural networks, multi-layer perceptrons. Um, and just to kind of point out, this happens at a token level. So, or a token embedding layer level. So there's no mixing between um, uh, these tokens. This network, there is a network, sorry, a feed forward neural network per token coming in. So we have a 1536 embedding coming in here, 1536 embedding coming in here, each of which is then flowing into its own network to learn these parameters given the context, because it already is being enriched by the other surrounding tokens through multi-head attention before then passing through this multi-layer perceptron feed-forward neural network to encode or capture some of this information. And again, just these weights and biases are all learned parameters. So these biases, these weights are learned parameters during that training process of BERT that I had walked through previously. And so the embeddings after the multi-head attention block are then again added back. Um, and so again, another skip connection. We do layer normalization again. Um, and this is again used to stabilize the training process. And this yields us another asterisk sentence embedding from the classification token. And this is an asterisk because it is still just one encoder block of the stacked several encoders in a BERT model, which I had mentioned is anywhere between 12 and 24, given BERT base or BERT large. And again, just a reminder, these earlier encoders are to capture things like short-term contextual dependencies, while these longer ones, or sorry, these later encoder blocks are expected to capture these more global, more complex interactions between tokens throughout sentences or sequences of text. And after we pass through these several other steps of the exact same process happening again, we get a several primed embedding that actually is the classification token, the sentence embedding that represents that phrase we initially passed in, I went to the riverbank. So I learned a lot in this process from a lot of these resources here in creating this lecture. If you're interested in digging into it a bit deeper, I highly recommend these different resources. Thank you very much for your time.